Yep, you're right.
The smallest of the atomic particles.
Yep. Yep. What else?
They're so small we don't even count them as part of the mass of the atom because
We can see that from here.
yeah,
Yeah.
they're tiny.
Very, very small mass, tiny mass, you're right.
They have a negative charge.
Mhm.
Yep.
In this experiment, we're going to be considering them as waves.
Yes, this is what I'm looking for. So in this experiment, we are considering these electrons as waves. But what is the key to know that? We need to compare the electrons with something.
Light.
With light. You're right. So light can do diffraction, can do interference, but the electrons, do you think that electrons can do that?
I would assume so, yeah.
Yeah, so according to this scientist, de Broglie told us that there is a relation between the wavelength and the momentum of the object. So actually, if we know the momentum of the object, it will be very, very easy to know the wavelength of the object. For example, if we have a car moving with velocity maybe 3 meters per second, and we know the mass of this car, it will be easy to figure out lambda. So how can we do that? Simply just calculate this, since P is equal to mass times velocity, which is the momentum. So this is the key, guys, to start today's experiment. And this experiment tells me that those electrons can experience diffraction. This is one of the light properties, but also the electrons can accept this kind of behavior. So in today's experiment, you will see this kind of behavior, guys. So we start the experiment, we start the electrons gun, and we receive those electrons, guys. So before anything, we receive those electrons on very, very small piece of graphite. And after that, those electrons will go and then be received here. If there is a diffraction, because we know if those electrons hit the graphite atoms, they will scatter, they will change their direction. If that can happen, so what we will see? We will see this kind of behavior. Each one of these rings will have a diameter d. So for example, this ring has a diameter d1, and the outer ring right here has a diameter d2. And I would like to ask you to come there so I can show you. So we'll stop this. It is 0. You can come here.
Sorry.
If I turn the light, I'm trying to see what will happen. So we should see the electrons being here as a green color. Yeah, you can come here.
I can see it.
Can you see? Perfect. Yeah. Just let me know if you can't see the rings. If I increase the potential here, you will see this kind of behavior. You can see those rings. Those rings are proof that the electrons can experience the diffraction, can have diffraction. What's the reason for that? The reason for that because those electrons hit the graphite crystal and then be reflected, as you can see. And the graphite crystal can work as the diffraction grating. The same work. There is no difference. We did that with light. We could manage to have the visible light colors, the spectrum, from sodium, from mercury. But even here, we can apply the same idea with electrons. If we start with de Broglie equation and then try to substitute P with MV, and then what do we need to do here, guys? We need to link, so kinetic energy is equal to 1/2 mv squared. That means v squared m squared is equal to, so we have 2m kinetic energy. And instead of having, maybe that will confuse you guys, so I will replace here with u, total kinetic energy. So now, if we replace P, which is mv, with the square root of 2mu, so that will give me what you can see right here, guys. So you can see that mv is equal to square root, and here we have 2me times. I'm sorry for that, we don't have electron charge. Just we have 2me times u. Okay, so that can help you to calculate the wavelength of the electron by knowing the potential, which is from the power supply that I changed. You saw that. This equation can help you to calculate the wavelength theoretically. And the equation that I provided you right here can help you to calculate the wavelength experimentally by knowing d, which is the diameter of these rings, the diffraction rings. And if you know L, guys, so what is L? L actually is this distance right here. So it's equal to 13.5 centimeter. And if I come here, I can show you L, guys. So this is L from here to here. So this is L, 13.5 centimeters. We know L, we know capital D. This small d that you can see right here, guys, actually represents the spacing between planes in graphite crystal. So we have two d's here. We have d2, which represents the distance between this family of planes that you can see right here. And we have another d that represents the distance between this family of planes that you can see right here. In this experiment, what we are going to do, we are going, guys, to prove that, we need to prove that de Broglie is right. He told us something right. And then we need to determine the wavelength of the electrons. So we can do that with the experimental equation, which is this one. And we can do that with the theoretical equation, which is this one right here that you can see right here. So after you finish this table, you can start the next table. So maybe here you figure out D2 with different applied potential. You can try to do the same thing with D1 and obtain different D1s with different U potentials. So once you get this table done, and by the way, how can you get lambda experimentally? You can get lambda experimentally from here. You can borrow this D from here. So I give you those numbers that we will double check by the end of the lab. So you can apply D1, that can give you lambda 1, and you can use capital D1 with that. And you can use D2 right here, so that will give you lambda 2, and you can use capital D2, which is this one, right here. Once you finish those two tables, and by the way, guys, once you compare the theoretical value with the experimental value, you will see that you already proved the de Broglie equation, so the de Broglie equation is right. Then, by the end of this lab, you need to determine the lattice plane spacing of graphite. Actually, you need to figure out this experimentally. and then compare them with the values that we have right here. How can we do that? You need to plot D1 with 1 over square root of u, and D2 with 1 over square root of u. And once you do that, guys, you will see that you have those two straight lines. One of them for D2, the other one for D1. Try to get the slope from this line and then slope from this line. So that will give you K2 and K1. What are K2 and K1? K2 and K1 actually are constants. By the way, I'm recording the session, so you don't need to take the pictures. K1 and K2 are constants that we need to have right here, guys. So here is a relation between D, the diameter of the ring, and 1 over square root of u. So that will give you this slope. And if you use this equation, guys, that can help you to figure out D. So from the slope, you know K, you know L. From here, I give you L. You know Planck's constant. You know the mass of the electron. You know the charge of the electron. I will double check if we have charge of the electron here or not, but I will double check it. You know, you don't know D. So since you know K, L, H, and M, so it will be easy for you to figure out D. So this is actually today's experiment. So it's not difficult, guys. And you can start working. So everything here is connected. Yeah, just need to change the potential U, and then try to use the caliper to measure the diameter. Do your best to get the diameter. If you can do that, you can do something like this, guys. Yeah, you can measure the inner diameter, and then you can use the outer diameter, and then try to figure out this distance right here, and then divide that by 2. So when you do that, you will have a value that can be added here and can be added here to the inner diameter. So when you measure the inner diameter and you measure the outer diameter, so that will give you 2 of these distances. So you can divide that by, so if the inner diameter here, dn is equal to 5 centimeters, for example, and if d out is equal to 6 centimeters, if I do out minus dn, so that will give me 1 centimeter. So that means this plus this, so that will give me 1 centimeter. So I need to divide 1 centimeter by 4, so that can give me this small distance here. So then I can add 0.25 centimeter to the left-hand side and the right-hand side of the inner diameter. Yeah, looks complicated, but you can do that, guys. So this is everything for today, and you can start. And for the report, I need these main titles, and I need this table, I need this table, and I need this graph, and also I need your calculations. Thank you so much.